2 million. That's a massive number, right? Well, that is the exact number of kids under the age of 5 who are rushed to U.S. emergency rooms every single year because of one specific virus. If you've ever just brushed it off as another common cold, that number should absolutely make you pause. We're talking about 60 to 80,000 hospitalizations and, tragically, several hundred deaths every year in the U.S. alone. This bug is incredibly common. Pretty much all of us will get it probably a bunch of times. But for the most vulnerable among us, it is way, way more dangerous than a simple sniffle.
Welcome to This Explainer. Today, we are opening up the Infiltrator's playbook to demystify RSV, or Respiratory Syncytial virus. We're going to find out exactly how this stealthy little pathogen operates, how it literally hijacks our cells, and the truly fascinating ways modern medicine is fighting back. So, let's jump right in.
Section 1. The Opportunistic Invader. Identifying the culprit.
So the name itself actually reveals a ton. Syncytial, pronounced syncytial. It comes from the Greek syn, meaning together, and cyto, meaning cell. Now that sounds harmless enough, right? Until you realize what it actually means inside our bodies. It means the merging of multiple human cells into one single, totally unnatural mass with multiple nuclei. Forcing cells together like this? Yeah, that's not normal, and it is definitely not a good thing. It's essentially the calling card of a microscopic hijacking.
How on earth does it pull this off? Well, RSV is kind of an enigma. It's incredibly tiny. We're talking about a single-stranded RNA genome with just 10 genes and 11 proteins. But the sheer efficiency with which it uses this tiny toolkit is wild. It has these specific attachment molecules right on its surface. You can think of the largest one, the G protein, as the primary lockpick. It binds the virus directly to the outside of the cells lining our windpipe. Once it's latched on, it gets an assist from the F and SH proteins, which basically act like breaching tools. They literally force our host cells to fuse together, creating those weird syncytia masses we just talked about. And if that wasn't enough, it deploys this non-structural protein called NS2. This one literally causes the infected host cells to round up, die, and just slough right off.
Section 2. How RSV merges cells. The stealth tactic.
Okay, imagine a hotel for a second. Standard viruses are kind of like criminals who break into a room, copy themselves, and then walk back out into the main hallway to find the next room. But when they step into that hallway, which is like the external space between our cells, they totally expose themselves to our circulating immune guards. But RSV? No way. RSV doesn't even use the hallway. Instead, it forces adjacent cells to fuse together. It's literally like knocking down the walls between the hotel rooms and just walking right through. By moving completely internally from cell to cell, the new virus particles stay entirely hidden from the immune cells patrolling outside. It is a brilliant, totally stealthy evasion tactic.
Section 3. The danger in the lungs. Collateral damage.
Let's trace the actual path of this infection as it makes its descent into the lungs. RSV usually starts up in the upper respiratory tract. And because it hides its replication using that cell-fusing trick, it quietly works its way deeper and deeper down into the lower respiratory system, specifically into the tiny bronchioles and the alveoli. This is where things get really serious. RSV actually triggers our basal cells, that's the layer just beneath the surface, to mutate into what are called goblet cells. And goblet cells have one main job: making mucus. Suddenly, there is this massive overproduction of mucus just flooding the airway, mixed with inflammation and pus from all those dying cells. When you picture this happening inside the incredibly tiny, narrow airways of a small infant, you can start to really grasp how completely overwhelming and terrifying this physical blockage must be for their little bodies.
And that brings us to a really crucial part of our immune response that, surprisingly, and honestly kind of ironically, actually ends up working against us here. They're called nets, or nuclear extracellular traps. As the virus invades the lungs, our innate immune system rushes in to help, sending neutrophils and macrophages to fight. But as these immune cells fight and eventually die off, their nucleic acids, primarily their DNA, spill out and just sort of accumulate. This ends up forming a literal physical matrix of sticky material right inside the lungs.
You can really think of these nets like a giant microscopic spiderweb. Now, against bacteria, this spiderweb is amazing. It holds the invading bacteria right in place so other immune cells can come in and destroy it. But during a viral infection like RSV, especially in the tiny airways of a baby's lungs, it acts like a spiderweb that catches literally everything. It traps all that accumulated pus, the mucus, the cellular debris, holding it all stubbornly in place. Babies just don't have the physical lung strength to cough out this sticky, dangerous mess, and their breathing becomes severely obstructed. It's a heartbreaking reality, and it is exactly why medical intervention is so often absolutely essential to keep these young ones safe.
Section 4. Why age matters most. Targeting the vulnerable.
When we actually look at our immune defenses, the vulnerabilities at the absolute extremes of life become super clear. In healthy adults, a massive part of our defense system relies on plasmacytodendritic cells, or PDCs. Think of these guys as the alarm bells. They spot the virus and immediately release interferons, yelling at neighboring cells to put their shields up. But in infants, these alarm bells are still immature. They just don't produce enough interferon. Second, we have our CD8 T cells. These are the killer assassins that mature in the thymus gland and destroy infected cells. Again, in babies, the thymus is immature, so the assassins just aren't quite up to the job yet. And then, looking at older adults, as we hit our 70s and beyond, those once powerful CD8 T cells just naturally begin to lose their effectiveness. So both extremes of life really lack the robust defense needed to quickly clear this virus out.
Now you might be wondering, hey, if we all get this as a baby, shouldn't we just be immune for life? Well, it turns out there's a fascinating catch here. Remember those F and G lockpick proteins on the surface of the virus? They aren't just your standard proteins, they are glycoproteins. The glyco part means they have a carbohydrate attached to them, and humans are notoriously terrible at building lasting immune memory against carbohydrates. The antibodies we do make, they tend to just fade away after a few years. We literally forget what the virus looks like, which leaves us wide open to getting reinfected over and over again. Because a newborn's immune system is so incredibly immature and struggles with those carbohydrates, they have to rely entirely on borrowed time, specifically borrowed antibodies from their mom. And the timeline for this is crucial. For the first 34 weeks of pregnancy, there's very minimal antibody transfer happening. It is really only during that critical window between weeks 35 and 40 that the bulk of the mother's antibodies are passed over to the baby in utero. Then, for the first 6 months of life, the infant completely relies on that borrowed shield. This beautifully, but tragically, illustrates why premature babies are at such a massive disadvantage. They miss out on that critical final transfer window, leaving them almost entirely defenseless against an RSV infection.
But we really can't forget about the other extreme of life either. Because our T-cell effectiveness drops off so much as we age, RSV is definitely not just a childhood illness. It's actually estimated that over 10,000 older adults in the United States die from RSV infections every single year. When the immune system is past its prime, this opportunistic little virus totally exploits the weakness.
Section 5. Fighting back against RSV. The counteroffensive.
But here is the amazing news. We finally have some seriously powerful weapons to fight back. First up, the FDA has approved 2 vaccines specifically designed for adults over 65, and these protect against both the A and B strains of RSV. Second, because we know we can't really effectively vaccinate a newborn directly, the go-to method right now is maternal immunization. By vaccinating the mother during pregnancy, she produces a massive surge of antibodies that she safely passes down to her baby in the womb, perfectly bridging that vulnerable 6-month gap right after birth. And finally, for high-risk or premature infants who unfortunately missed that antibody transfer, we have palivizumab. This is a brilliant lab-made monoclonal antibody that directly targets the virus's F protein, acting like a totally artificial shield during RSV season.
RSV is this ubiquitous, ancient pathogen that is just perfectly equipped to exploit the gaps in our biology. I mean, hiding from our immune system, flooding our lungs, targeting the exact times in our lives when we are the least protected. But by finally understanding its infiltrator's playbook, we are rewriting the rules of the game. It really makes you wonder, though, as medical science continues to build these entirely new defenses against ancient viral infiltrators, how will our own immune strategies continue to evolve in the future? Thank you so much for joining me for this explainer, and keep asking the right questions.